Okay, the next topic is the governing equations for reacting flow. The governing equations of reacting flow are conservation equations basically. So, they will conserve several quantities. Okay. They conserve mass of the mixture, mass of individual species, then momentum of the mixture, the individual species is conserved, then energy is conserved. So, these are conservation equations. So, we have to conserve in this reactive flow or in a combustion environment, we have to conserve mass, momentum, species and energy. So, we use partial differential equations to write the conservation of these quantities, and we actually write the equation and integrate over like for assuming a very small control volume, infinitesimal control volume is taken, and in this the conservation is made and partial differential equations are derived. Okay. So, main assumption what we make here is the continuum approach. The main approach is continuum approach, or which is called macroscopic approach. Okay. So, what is macroscopic approach? If you have, so you know that the molecule, there are several molecules of several gases present in the reactive system. Okay. If you want to trace each and every molecule and work like understand where it is located, what is the velocity with which it moves, etc., it is not possible for us to analyze anything. So, what we are interested in, we are not interested in the molecular level values or quantities, we are interested only in the average effect of these molecules. So, that approach is called macroscopic approach. So, what we allow here is we will take several molecules and only see the average effect of these molecules on several measurable, observable and calculatable properties. So, like pressure, temperature, enthalpy, everything. So, we can get this, but these are all not due to an individual molecule. We cannot go to molecular level, it is only an action of several molecules, average effect of all the several molecules put together. So, we choose a control volume and do the conservation of this. Okay. Now, this control volume where the conservation is done is smaller than the entire domain. For example, if you take this room, big room, we will only consider a say 1 centimeter by 1 centimeter by 1 centimeter control volume. So, it is much smaller than this room size, but this 1 centimeter is much larger than a mean free path of a particular molecule. So, molecule before hitting with another molecule, they travel at a particular distance called mean free path, but that length scale is much smaller than the control volume what you take into account. So, just giving some examples. So, in the macroscopic approach, we do not go into molecular level details, and we can use classical thermodynamic approaches here for solving our problems. Okay. Now, in a control volume, several molecules enter and exit through control surfaces of the control volume. Okay. So, control volume, you can actually take a Cartesian control volume, so delta x, delta y and delta z, Cartesian control volume, say cuboid, and so 6 phases are there through which molecules can enter and leave. So, those surfaces are called control surfaces. Okay. Now, when the molecules enter, they can transport mass, momentum, energy into and out of it. So, as a result of these transport, there will be changes within the control volume, there will be changes in these quantities as a function of time. So, this is the principle what we use for deriving the conservation equations, a control volume. So, you can see the control volume is shown here. As I told you, we have taken the Cartesian coordinate. So, this is x direction here, x direction is horizontal direction, vertical direction is y direction here, and z direction is the mutually perpendicular direction z. So, there are 6 phases. Let us take the x direction for example. In this phase, perpendicular to this phase, the x direction, this phase is prevailing and this phase, there are 2 phases. So, this is m dm by dt. Let us take first mass is entering, some mass is entering. This is m dot, and at the station of x it is entering. So, we say m dot x, kg per second. That is the mass entering here, and the mass leaving at the station x plus delta x is given by dm by dt at x plus delta x. That is written like this. So, this is also kg per second. So, this is in the x direction. So, similarly we can write for the mass entering through the bottom face is dm by dt y, and that leaving the top surface is dm by dt y plus delta y. Similarly, the x direction dm by dt z and dm by dt z plus delta z. Okay. Now, if the net mass entering, okay, that is dm by dt x, dm by dt y and dm by dt z, okay, that is same as the net mass leaving dm by dt x plus delta x, dm by dt y plus delta y and dm by dt z plus delta z, then there will be no accumulation of mass in this. Okay. But if the net incoming mass is higher than the outgoing mass, then mass will accumulate with time. So, if you say dm Cv of control volume, this is control volume, the rate of change of mass of control volume with time, this will be greater than 0 if m dot in, I will say sigma m dot in is greater than sigma m dot out. Okay, or we can simply write dm Cv by dt will be equal to sigma m dot in minus sigma m dot out. So, the simple mass conservation. So, this in this form we are writing, but when you translate this and write the entire equation, you will end up in a partial differential equation. Okay. So, this is about mass. Now, instead of mass multiplied by velocity, that is momentum can enter through the surfaces. Similarly, momentum can change within the control volume. Similarly, energy can enter. So, this mass into specific energy that can enter and leave through other surfaces, so that the net energy of the control volume can increase or decrease based upon the entering and leaving quantities. Okay. So, this is the control volume approach where we seek the flow through surfaces of control volume in and out, and try to write the conservation equation for the particular quantity. So, mass, momentum, energy, species, etc. Now, let us first see the species conservation. So, detailed derivations are not given here, but we will understand physically the terms involved. So, for example, conservation of species, one of the species, let us say, we have to actually do several species. For example, if capital N number of species are present in a mixture, at least we have to conserve n minus 1 species. So, let us take a particular species, say species A, and try to write the conservation equation for the species. Okay. So, this is written as partial derivative of the quantity rho Ya. Rho is the mixture density into Ya is the mass fraction of the species. This is the mass of the species. So, rho into Ya will be equal to Ma, mass of the species A. The rate of change of mass of the species A with time, correct. So, that is written here. This is per unit volume, this is actually run per unit volume basically. So, that this is actually not Ya, this is actually rho A, sorry, this is rho A. So, rho A into V if you put, you get Ma. So, now this is written per unit volume. So, rate of change of mass of species A per unit volume is this term. Okay. Now, that is equal to that plus the convection. When the species comes in, it comes in with this, there is a flux for this. So, we know this, correct. So, rho A Va equal to rho V Ya minus rho diffusion coefficient of A into the mixture into dYA by dx in the x direction, let us take. So, this is the net mass flow rate of A per unit area of cross section through a particular phase. So, when you try to do this and take the sum of all, you get this term. So, due to the convection of the species through all the phases, Okay. This convection, first what is the net mass convected away minus the net mass coming in, that term is called the second term here. This convection actually involves the species velocities. Okay. What is species velocity of A? The bulk velocity, velocity vector, bulk velocity plus diffusion velocity of A. So, this species velocity, so this term here represents the species velocity vector of A. Okay. So, with its own velocity, it is convected out of the control volume through some surfaces and converted in through some surfaces. The outgoing flux, that is mass flux, is what? Mass flow rate divided by the cross sectional area minus incoming, that net mass F flux, that is outgoing mass flow rate divided by unit area minus incoming mass flow rate per unit area. That term is the second term here. It is called convective term. So, this term is called convective term. Basically, in this particular case, it also includes the diffusion. Okay. The convective term also includes the diffusion. This actually, because why I say it convective term, because it involves the species velocity, but species velocity itself has two components: the bulk convection of the mixture and the diffusion of the particular species into this mixture. Okay. So, the rate of change of the mass of the species per unit volume plus the convective, the net efflux, mass efflux of the species to the control volume will be equal to the rate of production or consumption of the species. It can be positive or negative, this omega dot this. So, this has a unit of kg per meter cube second, and this is actually written as some coefficient into concentration of species A, concentration of species B, etc. Some reaction rate, net reaction rate, it cannot be one equation, maybe several. So, what we saw in the previous lecture, d concentration of O2 by dt involving say 4 reactions, 3 reactions and several forward and backward reactions, etc. So, this is net rate of production or consumption of a species A. So, that can be written in this kg per meter cube second. So, the conservation statement is rate of mass of species A accumulated in the control volume. So, please add per unit volume plus the net mass F flux, that is outgoing flux, outgoing flow rate by unit area is called outgoing flux, minus incoming flow rate by unit area of species A through the surfaces of the control volume is equal to the net rate of its production or destruction, denoted by the term in the right hand side, omega dot triple dash A. So, triple dash actually represents per meter cube. So, every term is per meter cube per unit volume. Okay. So, the net efflux, mass efflux of species A is convection term basically, because it involves the convection of the species velocity of A. But this species velocity is calculated using the bulk velocity, mixture convection plus the diffusion velocity. So, this is the species conservation. So, we have to understand that n minus 1, if n multi-component species are present, so n minus 1 reactions are going to be solved like this with non-linear source term. So, this is a non-linear term. This term is a non-linear source, A into exponent of minus AB RUT. So, that exponential dependence on temperature is present. So, that becomes very highly non-linear source. Okay. So, as I told you, when there are n components, n minus 1 species conservation equations are used. So, that is why we use that steady state approximation or partial equilibrium approach to reduce the number of species, to the number of species to be solved using a partial differential equation. So, this is a partial differential equation. So, here written in partial differential equation written in vector form. Okay. Now, the nth species is calculated by using this identity. So, sigma yi is 1. So, the mass fraction of nth species is calculated using this identity. The nth species normally will be kept as inert species such as nitrogen. Okay. Nitrogen will not react much, so that will be the nth species. So, we need not solve for the transport equation for that, just calculate using the identity. Okay. Now, if this is for one particular, this equation is for one particular species, say A. Now, add for all the species, n species, write this equation for all the n species and add them, you will get the conservation of mass of mixture. Do you understand? So, conservation of the mass of each species, okay, is summed up for all the species, will give the conservation of mass of the mixture. Okay. So, what happens to the, let us say take the right hand side now, right hand side, what happens to the right hand side, there is a term called omega A triple dash. So, now you sigma it, okay. So, A going from 1 to n, okay. So, this will become 0. How? Because the net reaction rate of the reactant species, which are consumption negatives, they are negative values, cancel out the net reaction rate of the product species, production rate positive. So, they will cancel each other, so that you will get the sigma omega triple dash I equal to 1 to n will be equal to 0. Okay. So, that is going to eliminate the source term. So, you will see that there is no source term in the conservation of mass of mixture. This is what this. Okay. Now, if you take the diffusion fluxes, so we are now having only this velocity here, but what about the species velocities? Diffusion, due to diffusion. So, here this velocities, so VA diffusion velocities. So, what happens to that? The diffusion fluxes of all the species is also going to be 0. Sum of the diffusion fluxes of all the species, when summed up, they are going to be 0. So, that will eliminate that diffusion velocity appearing in this. So, we get a simple equation for conservation of mass of the mixture, which is nothing but the partial derivative of rho into volume, that is the mass, the rate of the accumulation of the mixture mass inside the control volume. So, rho into V per unit volume is rho V by V is rho. So, that the rate of change of mass of the mixture, rho V is the mass of the mixture per unit volume, plus the net efflux of the mixture which is transported out of the control volume per unit area, minus in coming the mass which is coming in, mixture mass which is coming into the control volume. So, continuity equation represents the overall mass conservation, mass of the multi-component mixture accumulated within the control volume, the transient term, the first term, time dependent term, plus the net efflux, that is the outgoing mass flux minus incoming mass flux of the mixture. So, net efflux of the mixture mass through the surfaces of the control volume is equal to 0. That is the simple continuity equation what we have here. Continuity equation or conservation of mass, okay, mass of the mixture. Now, some points to ponder. For reacting flows like observed in burners, okay, and stoves, the velocities are very low. We do not have very high velocities. Okay. So, even if you have a turbulent flow, velocities are not very high. Okay. So, Mach number will be very low, say less than 0.3. So, the flow is assumed to be incompressible. The main see why I am saying this here, because if you go back, you have this term here, the rate of change of mixture density with time. Okay. So, why this? So, normally when the velocities are very low and the flow is incompressible in nature, people will think that the density will not change at all, density is constant. So, incompressible flow density is constant, that will be the thinking. But here this term is important, we cannot neglect this term, because even though the flow is incompressible, okay, the temperature dependence is there, and also the species will be changing, the concentration of the species in a particular location and the temperature at a particular location will be changing. Similarly, with time also the concentration and the temperature will vary. So, this term rate of change of mixture density with this time is due to the change of temperature and composition of the mixture. So, that is, so even though the flow is incompressible, density is not constant, density will vary as a function of temperature and composition of the mixture. So, that we have to understand. So, next equation is the momentum conservation equation. So, momentum conservation equation actually follows Newton's second law of motion. For the fluid, we can say the rate of change of momentum in a control volume is equal to the sum of all forces acting on the control volume. So, that is the simple statement what we can make about this. Okay, now what is in the left hand side of this equation? This is momentum equation, again compactly written in the vector form. So, now see that the first term is already we have discussed a lot. This is the momentum, rate of accumulation of momentum of the mixture in the control volume. So, rho into V vector, that is the momentum in a particular direction. So, this is a vector. So, we can resolve it into 3 directions. This divided by the volume. So, rate of change of momentum. So, this multiplied by volume divided by volume. So, this will be the momentum mass. Rho into volume is mass into velocity, that is momentum per unit volume. So, rate of change of momentum per unit volume in the control volume, plus this is the convective term, again the net efflux of momentum. So, rho V A, across the surface only this happens. So, rho V A is the mass flow rate of the mixture into its velocity V, that will be the momentum. So, you can again resolve into 3 directions. So, rho V into cross section area. So, when you do again by divided by volume etc., or write in gradient terms etc., you will see that this is going to be the efflux of momentum, that is the outgoing momentum flux minus incoming momentum flux across the control surfaces in the control volume. So, convective term. So, this is the storage term or accumulation term. We can both lot of nomenclatures are there. It is accumulation, or we can also say time dependent. So, time dependent term or accumulation term or storage term, anything can be used for the first term, where within the control volume there is a rate of change of the momentum as a function of time. So, this is the left hand side, rate of change of momentum in the control volume though, and through the control surfaces, across the control surfaces. So, net rate of change of momentum is in the left hand side. The right hand side, forces. First term is the del ditto tau. This is the gradient of stress tensor. Stress tensor will show you next slide. So, this is gradient of stress tensor. So, this will involve the normal stresses and shear stresses, okay, acting on the control surfaces, and these are the forces due to the viscosity of the fluid. Due to the viscosity of fluid, these stresses are appearing. So, due to pressure, the pressure gradient, so due to pressure forces will be added, that is represented by the pressure gradient here, and some body forces, okay, that can be absorbed in this term B vector. So, body force vector is the B vector. So, these are all force terms: surface force, pressure force, body force. This is volumetric. So, surface forces are due to viscosity effects, both normal and shear stresses are included here, pressure based forces and the body forces. So, rate of change of momentum in the control volume and across the surfaces of the control volume, the net rate of change of momentum is equal to the forces acting on the control volume surfaces and within the control volume. Body force is a volumetric term. Okay, now the B vector is nothing but the force. So, Fk is the force, volumetric force per unit mass, volumetric force per unit mass on a kth species. Similarly, you have to add for all the n species. So, mass fraction of the species into the force acting on the species, that summed up into the mixture density will give you the body force. This will be added, but this will be negligible actually. So, this actually in several cases will be negligible. So, this is the body force term that can be added. If you want to add, you can add it. Then stress tensor is like this. So, you can see a stress tensor, you have normal stresses. So, for example, here tau Xx. Similarly, there opposite also the same pattern will appear. So, symmetric nature, this is symmetric in nature. So, normal stresses are tau xx, tau yy and tau zz, and the stresses which are tangential to the surface. Okay, for example, here tau xy and tau xz in this plane. So, in the top plane tau zx, tau zy, they are parallel to the surface. Similarly, in the other side you get tau yz and tau yx. So, all these contribute to shear stress. So, the tangential components add to the shear stresses, normal component add to the normal stresses. Everything can be written in terms of viscosity. So, this is the dynamic viscosity. So, the stress tensor in the tensor form is written in terms of the gradients of velocities, velocity gradients and viscosity. So, you also use what is called a bulk viscosity or secondary viscosity, which is actually negligible in several applications. So, this is the shear stress and this is normal stress, and so this is actually equal to 1, sorry, this del ij will be equal to 1 if I equal to j, or equal to 0 if I is not equal to j. Okay. So, now this is the stress tensor, and which is written in terms of gradients of velocities, velocity gradients u, I, u, j, u, k, etc. are the velocity used here, and these are all directions. Xi can be x direction, xj can be y direction, xk can be z direction, and so on. Mu is the dynamic viscosity, and mu dash is the secondary viscosity. So, this is the viscous term. So, once you know the viscous term, body force term, pressure is known. So, the entire equation can be formulated. So, this is the entire equation. The forces due to viscous effects, this is the pressure induced forces, pressure gradient, and the body force, volumetric, and this is the stress tensor here. Okay. So, I will stop here. So, we will continue with energy conservation from next class.